Hi everyone, this is Ken Fridley. I'm the product manager for Greenlee Communications Ethernet and Transport Line, and welcome to Smart Testing for the Smart Grid, brought to you by Greenlee Communications. Today we're going to talk a little bit about smart testing for a smart grid, the different types of testing that's currently being done, what could be done, and also kind of look at how the network is evolving as we move from a traditional grid to a smart grid. So we look at the grid evolution. In the past, it's been a very, very typical one-sided type situation where we're transmitting from a legacy substation or distribution to a system operator. It was very, very manual. It was mostly combined of 2- and 4-wire sensors, POTS type testing, plain old telephone system signaling, legacy transport type systems, and mostly around T1 timing synchronization. And as you can see, most of the communications was one directional. We had some communication back and forth between substations, and we had communications from those information, that SCADA, going back up to the distribution control center or the transmission control center. So very easy communications, still complex, but heavily reliant on old DS1, DS3 type technologies. What we're seeing now in the future as we move in and start developing more and more smart grid systems is that there's a need for advanced service testing. And the reason why is that we now have distributed intelligent electronic devices, mesh networks. We're using more voice over IP for voice communications instead of the legacy type TDM type voice. Now using IP cameras and access control. There's a huge migration over to Ethernet and MPLS and even wireless technologies. And we've moved off of DS1 type timing synchronization over to using Y1588 version 2 for precision timing protocol synchronization. And most importantly is if you look at your data flows here, your data is now moving not just between substations and the control centers. It's a huge amount of sensor arrays all the way out to the customers, commercial customers, residential customers, and even all the way out back to the actual energy storage devices. So we have a lot of data that's communicating back and forth with each other. So simple type testing that we used to do in the past really doesn't apply in the future. So that's what we're going to talk about today. So we look at some key drivers that's driving the smart grid testing. What's interesting is that a lot of our grid infrastructure is aging. A majority of it is 40 to 60 plus years old. It's becoming increasingly inefficient and unreliable. There's a huge reliance on non-renewable fuel sources like coal, oil, and it's also designed to manage the legacy transmission and distribution schemes, which is just like we were talking about, where we're transmitting data back from, say, a generation into the control center, or from the distribution on up into the control center, but it's very one-way or limited two-way type communications. And so right now there's a radical transformation that's underway. We're doing a migration over to new renewable low-carbon sources such as photovoltaic. Hydroelectric is still important, wind generation is important, and even thermal type generation. And a lot of those low-carbon sources are being distributed now. Rooftop solar, for commercial buildings, residential customers. Great benefit for distributed generation, but there also brings challenges, say that when the wind doesn't blow or the sun doesn't shine, those type of generation facilities are sometimes not matched to the demand. So that brings in its own challenge of being able to monitor that type of data and that type of generation. And also an intelligent communication infrastructure. As I mentioned in the opening is that we're talking Ethernet, a migration off of the legacy TDM type services over to more modern Ethernet MPLS type services. So there's a huge intelligent communication infrastructure being pushed. In fact, 70% of utilities plan to expand field data collection in the next 3 years. So, we're moving from a very simple system to a lot more device connectivity, data aggregation, analysis, more toward a smart utility, and then an integrated infrastructure where utilities talk to other utilities. And we're already doing that today, but we're going to see a lot more in the future. So a lot more connectivity and convergence in the data structures. And the reason why is that we all agree we have to improve operational efficiency. Have to make sure that the energy is produced when demand is highest and is scaled back when it's not. We have to reduce operating costs. We have to make sure that if we're sending out technicians for a communications issue, that we know where that issue is, we send them to the right place, and we get them to resolve that issue immediately and prevent those non-productive dispatches. Also, with modernizing the infrastructure, again, the advanced sensor networks, the edge device visibility, the ability for operators to see what's coming in, the type of demand that's coming in right from their consumers, and also what's going on from their generation facilities, and also distributed generation. What's going on with that rooftop solar? What's being fed back into the grid? So being able to have that edge device visibility. And again, a migration to an all IP network. It brings its own challenges because there's a lot of the legacy sensors that are still out there that are being migrated over from an analog more to a packet-based. So there will be a large migration as well. And again, the ability to perform big data analysis. And I know that's the big buzzword in the industry is big data, but it's the collection of all those sensor arrays and getting real-time operational analysis data off of that so that you can make intelligent decisions about when to generate power, where is it going, and what to expect from the demand from the customer standpoint. And by doing so, it enables system operators to improve the reliability and security. It optimizes their operational costs, manage the entire system as an integrated unit, not just among one system operator, but among multiple system operators so that they can share data back and forth and understand what's going on in the entire grid. So they can actively sense and respond to a system, to your customer's demand, to your supply, even storage. As we move into large-scale storage devices, now they're becoming economical and being deployed out in the network, we need to understand what the status is of those storage devices, what their capacity is, what their load is. Are they online or are they offline? And also, cost, how to drive cost out of the system. What's the cost to generate? What's the cost to distribute? What the customers are demanding, what they're paying as well. So getting that information back and forth is very important. So if we look at some of the smart grid data sources, from a demand side management standpoint, obviously advanced metering infrastructure, the AMI that's being pushed out, the HAN, the home area networks, your demand response, your load management, being able to see where that data is coming from. There's a lot of sensors out in the network now, from capacitive banks, reactive banks, your generator, your point sources, and also the distribution automation. Now we have integrated IEDs that are producing SCADA data, monitoring data, and feeding that back to the network. Synchrophasers that are gathering that information, pushing it back to the network, so we have greater visibility into what's going on in the network, how's it working. And that feeds into intelligent relays and controls too. So we have very quick trip and reset and intelligent resets, and understanding that when one substation goes offline or one circuit goes offline, how does that impact the rest of the network? And where do we go? How do we adequately load shed or load balance to make sure that the most customers stay online for the most amount of time without having complete blackouts of entire regions? And again, the distributed generation, some of the challenges there. It's great that we're seeing a lot more rooftop solar or wind generation, but the problem is that there are clouds in the sky, and when clouds obscure photovoltaic cells, voltage goes down, output goes down. So by marrying climate information, we understand that there are clouds in the sky and we know what direction they're moving in. If we know where our photovoltaic cells are, rooftop solar is, we can now understand and model, if we have that sensor information, where that peak demand and that peak power is going to be as it rolls across the network. So we can proactively plan for and react to those types of power variations. So this is driving a lot more data into the network. It is enabling big data analytics, but it also brings in big data across networks that may not have been designed to handle all this extra network data being generated. So if we look at some of the smart grid data sources we're already talking about, but here we have our traditional generation, transmission, And that is generating data about what's going on in the plant. How are we controlling our plant? How are we optimizing our flow, hydroelectric flows? What type of generation is going on based on customer demand? And that's being fed into the PLC data, the SCADA data. Now, this is showing routers, so we're talking about an all Ethernet network, but this is actually a combination of still TDM. There's a lot of SONET out there in the network still. There's a lot of DS1, DS3, or SDH. So, you know, we're looking in the future, this will be more and more of an IP-based network, but there is still a hybrid data flow of that information. It's coming in, may not be coming in from Ethernet, but it may be transported over Ethernet, or Ethernet data may be tunneled inside of a SDH or a SONET network. So, you know, we're seeing this network, regardless of the physical medium or the transport medium, there's a lot of data that now gets fed in to the network. And we've seen this type of information for years, decades. Same way with their substation data. A lot of information that gets passed back and forth. SCADA type system control and data acquisition. Your 61850 type goose type messaging that's now interconnecting different substations and controlling the trip and reset and the flow. So if we look in our network here, as we move over to more of an IP-based network, we're seeing that your operational data, your production, or your protection, your SCADA management, a lot of the RTU, IED type information, PMU type data information, this is increasingly becoming packetized and being fed into a substation router, which is then fed up and either shared with other substations or information that's set up into the actual network operations center for management and control. Also, though, inside your substations, we're now seeing that there's more non-operational type data that's being generated, information that we didn't see in the past. So a lot of the AMI type information coming in from customers' homes is very low and slow type information, data information that's being sent up via RF and being collected in a meter concentrator inside the substation. And that information then gets aggregated and sent upstream from there as packet information. But we also have our demand response, distribution management type data flows, and even security. So we're now collecting IP camera type information, and that becomes a data flow and gets pushed across the network. The enterprise data, technicians that are based out of the substation or go into the substation as a work location or to perform work, they need to get on the internet, or excuse me, the intranet, to send emails or get in emails or access documents. And also the ability to do intranet voice and data so they can communicate to the network operations center or amongst themselves too. So a lot more information that traditionally wasn't in a substation is becoming more prevalent as substations evolved. So now typically your substation router, your operational and your non-operational information is completely siloed. Sometimes, depending on the CIF or NERC standards that you're implementing, it could be two completely separate networks, or it's separated by VLANs or MPLS tags. But regardless, your operational and non-operational data is always siloed away from each other and not allowed to intermingle. One is, high security, absolutely must high priority type information, where the non-operational information is typically a lower priority, takes a lower class of service. And then as we go out, we look at even in the customer network, distributed, the microgrids, your commercial microgrids and cogeneration facilities that feed energy back into the network. Those advanced networks are providing data now to the network operators, system operators, to be able to see what's going on in the network. We now have vehicle charging stations even, or users machine to machine, or the Internet of Thing, another buzzword. A lot of sensor information that's able to be shared across from a customer's home into the network from an API that allows greater visibility, not only for the customer to see what they're spending on energy, but also what type of demand is coming from the customer's home. So we'll see a lot more of that information. Also with distributed generation, again, the photovoltaics and the solar, or excuse me, the wind generation. And now with energy storage that's starting to occur in customers' home that may feed energy back into the network. We'll need visibility into that data, and that will occur in the future. And then finally, your adjacent ISO networks, your system network operators that are sharing not only your information with them, they're sharing information with you from an operational standpoint to make sure that the energy flows across grid boundaries as well. So lot of smart grid information that's going to be occurring not only today, but even more so in the future. And this is the reason why we're driving demand for Ethernet, because Ethernet has the bandwidth to handle this type of data flows. Now, as we say, inside every silver lining, there's always a dark cloud. So it's great that smart grids are evolving, that we're getting a lot more sensor information, we're getting real-time operational information. But with that, some of the challenges you're going to see is that the real-time status is absolutely critical. So to have real-time status information across your networks, you're already doing that today, but even more sensor networks in the future. Dense sensor arrays, a lot of different sensors feeding information in the network provides a lot more data going across the data pipe as well, and a lot more testing that goes into that because there's more issues. It has to be routed properly, has to be quality of service and class of service has to be set properly, and PLS tunnels have to be set up properly. Another challenge that you're seeing is that the proprietary protocols limit interoperability. In fact, one report that I was recently reading said that there's over 360 plus proprietary protocols used in the energy industry right now. So, each vendor has a proprietary protocol that they may have implemented in their sensor arrays. And so if you want to talk to that sensor array, you either have to use their proprietary protocol or you have to tunnel it across or convert it into something that the system understands. And so we'll see that continue. That's normal. But with the Ethernet and IP push now with sensors as we move forward, I think we'll see is that more and more of these sensor arrays will become Ethernet standardized, and actually that Ethernet IP will be pushed all the way out into the substation, right up into the synchrophasers and PMUs and IEDs that will talk native Ethernet, and so we won't have the interoperability challenge anymore. Part of the complex communication requirements also is that each one of these sensors has various bandwidth requirements. Everything from, say, 16 kilobits every 5 minutes for AMI, all the way up to maybe 1.5 megabits per second for a syncophaser that's in active mode that's continuously sending information across the network. Obviously, that type of operational data has very high priority standards, very low latency, and very high uptime requirements. Whereas some of the non-operational traffic, best effort Ethernet, intranet type access, higher latency, less availability is absolutely required. So, if we look across the network, there's a whole mix of data that's going across that makes it a challenge. We can't just test for one thing anymore. We have to be able to test for multiple type data flows going across the network. We also have to be able to test for rapid fault self-healing as well to make sure that when the network goes down, it adequately switches over to protection circuits in a certain amount of time so that availability of that operational data does not drop or does not cause false trips. We also need the ability to test this in service. We can't use a test mechanism where it takes the entire service pipe out of service while you test. You have to be able to test while you're in service. And again, part of the smart grid data challenges is migrating from a transport to an IP-based network. Traditionally, we use a lot of TDM, SONET, SDH, DS1, DS3 type networks, moving over from those into more of an IP-based networks. Sometimes it requires a forklift upgrade of equipment. Sometimes it takes a hybrid approach that slowly phases over to an all IP, but it brings its own challenges to how we make sure that we keep that information flowing without dropping a critical link. So now we talked a little bit about the market drivers, what's driving smart grid technology, some of the challenges that operators face with testing that or maintaining that type of data flows. I want to talk a little bit about traditional testing with a system called RFC 2544. So RFC 2544 is very well known in the industry. So in a nutshell, though, what is RFC 2544? Well, it was a benchmarking methodology for network interconnected devices. So this goes back to it was a benchmarking type protocol. It wasn't a a full standard that said this is how we're going to test the network. It was originally designed to benchmark individual network elements to say this router is performing per the specifications of the router vendor, or this switch is operating per the standards or specifications, and allow users, consumers actually to say, okay, I prefer this switch or this router over this other one because it closely matches the specifications of what I'm looking for. It wasn't specifically designed for network testing, even though if we look at the RFC document, it does mention about networks under test instead of devices under test. So, but there was never specifically said this is how you're going to test the network. It was just a general benchmarking. But it became the de facto standard for operators, not only system operators, utilities, but also telcos and cable providers. We didn't have anything better, so it was a system that we used. Now, it does define standardized tests and reporting mechanisms, such as testing for throughput, testing for latency, testing for frame loss. We call burst testing or back-to-back testing. All very important tests. We absolutely have to know how much data we can get through our pipes, so throughput is important. We have to know how long does it take for data to get through our pipes, that's our latency. We have to know how much data doesn't get through to the other side, that's frame loss, very, very important. So that's the reason why it kind of became the de facto standard, is it matched what we were looking for testing. One of the challenges, though, is RC 2544 is really kind of designed for point-to-point testing, to be able to go from point A to point B, occupy the entire pipe, fill it up to 100%, see where either the device fails or the network fails, and then benchmark where that failure is. And if it can't pass 100%, can I pass 90%? Can I pass 80%? Okay, I can pass 70%. So it's designed for testing those point-to-point networks or devices and test them to failure. It is intended to be an intrusive test. So, that's great if we're testing a dark fiber or talking about a service that isn't in play yet. But if we're trying to put another sensor array on task across an existing network, we really can't take the network down even at midnight in a maintenance window, because our networks are 24/7. Our sensor networks are 24/7. So still a very important test for some types of test scenarios, but really around the smart grid testing, probably not the best solution still anymore. Now, part of the reason why, it is still a strong contender. If we go out and talk to folks about testing, RC 2544 is always in a conversation because it's well understood by the industry, and a majority of folks use it. And we're used to getting a very clear report that says things pass, and I get pretty graphs that tell me that everything passed. And so from providing that to a customer, it's a great test because it kind of packages that birth certificate into a nice, pretty package that we can hand to a customer. And I think this is the reason why it's become the de facto standard in the industry. Now, some of the challenges we have, though, with 2544 or RC 2544 is that because we test throughput separately, and we test latency separately, and we test frame loss separately, and we test for a mix of different frame sizes, to do that per the standard, we're looking at a 7.5-hour test, which no one does, right? We know that we don't test all the frame sizes anymore because that reduced time to test. We don't do the full 20 different latency cycles because it doesn't need to be done. We're usually breaking that down to, say, 5 cycles or 3 cycles just to make sure latencies work, is within bounds. We may not even be performing the back-to-back or burst test anymore. So already we're taking a standard that was specified how to test a device under test, not a network really, and paring it down to fit into our scheme that we're looking for. So, it shows that it's already kind of a little long in the tooth. It's also an intrusive test. Again, talking about RC 2544 is designed to fill a pipe all the way to 100% and test it until it can't work anymore, and then back down and keep on testing until we benchmark it. It also really doesn't address the smart grid type requirements. We don't separate testing operational versus non-operational data emulation. Are we making sure that the data gets across with the right quality of service or class of service? And it's also not designed for multi-point destination testing. And we know that substations communicate with other substations, and simultaneously that same information may be sent up to the network operations center or even the transmission operations center. So we already have a lot of visibility into where this data is going when it goes across multiple points versus testing to a single point-to-point. It also doesn't take into account service availability testing. How long is the circuit up? Do I take any loss of sync? Do I take any pattern loss? Am I taking any type of service disruptions? All those classic type network tests that we can do with TDM right now, with DS1 and with Sonnet and SDH, we know how long the service is up and when it's available, and we have metrics for that. RC2544 really doesn't take that into account. And again, we need to be in service testing now. We can't take a circuit completely out to test unless it's a brand new circuit. So with that, what we'd like to do is take a look at some smart testing, and in smart testing of smart grids with Y.1564. It's an ITU-T standard. It's been out for about 3 years now. It's increasingly gaining acceptance with service providers, with utilities, with communication, cable MSOs. And so we want to take a few minutes and just explain what Y1564 is, how it works, why it's better, and how we can use it in a utility, and show an example of how we can actually use it in a utility network to test those sensor flows. So like I said, Y1564 really is vastly superior to RC2544. One, it tests multiple service flows simultaneously. So we can now emulate these syncophasers, PMUs, IEDs, non-operational information like IPTV and Ethernet traffic. We can support each one of these service flows, can support a unique quality of service and class of service, plus bandwidth limits. So if we say that an IED is only going to transmit at 64 kilobits per second, then we should be transmitting at 64 kilobits per second to make sure that that operational data can get across at that speed, and yet still be able to say, I want to test a syncophaser that should be transmitting at 1 megabit per second, and that can get across, and that priority is higher versus lower based on non-operational type data. So it's already superior to RC2544 right off the bat because it has the ability to do that where 2544 doesn't. It's also designed to test real-world situations. We're going to test the entire service path rather than a single point-to-point. We can test between substation and substation and also emulate sending that same flow from a substation up to the network operations center, or from one point to multiple points, multiple substations if we want to. And we're testing what's now known as a service level agreement, or an SLA. So we're not testing to network failure anymore. We're testing to, based on the profile characteristics of this sensor, let's test that sensor and its quality of service requirements and bandwidth requirements versus testing the entire pipe until it falls apart. It's also faster. Standard Y1564 test from a performance test standpoint is 15 minutes is recommended, but there is no specific minimum. So I've seen operations where they can run a Y1564 in as low as 5 minutes just to do a quick spot check on the network, or you can run it 24 hours just like you do with a BERT or an RC2544 if you want to too. Latency tests are no longer a separate test. It was completely redundant to do a throughput test where we could measure latency and then turn around and measure latency separately. So now with Y1564, it's combined into the actual throughput or BERT type test where we're measuring latency on every single frame that's sent and then reporting on that. And it also allows us to do in-service testing at times when the service level agreement should be met. We're not testing at midnight when our test operation window opens up. We can test at 3 in the afternoon if we want to, or 8 o'clock in the morning, because we're testing specific service level agreements for specific types of devices. And it also adds frame delay variation or jitter measurements. Now, our RC2544, folks may be saying, hey, I can test jitter in RC2544. And test equipment manufacturers have added that over the years at the request of customers. Not part of the original standard, though. Jitter was never taken into account when testing RC2544. So that's an evolution, even showing that 2544 had to be adapted to meet what we needed. Now, as you can see in this graphic, we're actually able to test multiple destinations with Y1564. Going back to what I was saying earlier, we can now test a point going down to a network operations center, and we can also test a point possibly over a microwave backup link, and we can also test across that main Ethernet or OC type ring out to the far end of another substation. So it allows us to emulate how those service flows are actually going versus just a point-to-point. So to do a Y1564 test, it's a little different than RFC2544, where RFC2544, we perform the same test over and over again with different frame sizes. What we're going to do with Y1564 is it's composed of two separate tests. First is a configuration test, and what configuration does is it validates each one of those sensors we're emulating or data flows that we're emulating. We're verifying that that is set up correctly and that each service performs as it's designed to a service level agreement. It provides simple pass-fail verification just to make sure everything's configured properly, and also say routers aren't connected properly, that's not allowing certain data to pass, we'll know immediately on a per stream basis instead of an entire pipe. So that allows you to troubleshoot this individual services before you put the whole network into play. Then once it tests each service, and those service tests can be as low as 5 seconds up to 5 minutes if you want. After that, then what's going to happen is your performance test is going to verify all the services and make sure that they perform as designed as well. Sorry, let me just move that over. So the performance test can run as low as 5 minutes, and it can run all the way up to 15 minutes, 24 hours if you want to, or longer. And once that's done, then what's going to happen is that we're going to provide a service level agreement burst certificate that's a general report just like on RC2544 with nice pretty graphs and all the per stream summaries and pass-fail status. So we're really not giving up anything from 2544 from a reporting standpoint. We're actually gaining a lot more because now we can generate multiple streams of information and get statistics per stream simultaneously, where you'd have to do that separately one by one if you're still using 2544. So it's much more intelligent. So from an overview, each service flow, it supports a unique frame profile. So when we look at frame profiles, what service layer? Is this service going to be a layer 2 service or a layer 3 service? Is it going to use VLAN? Is it going to a particular destination, and what destination is it going to? What type of frame size is it sending? We know that VoIP traffic takes a very small frame, where Ethernet traffic, general intranet email type stuff can use a much larger MTU. So each one of these streams can have a unique frame profile. It can have a unique bandwidth profile. So we can send individual information rates. We can have different priorities of flow, where those different flows or where those different services are going. And we can also define individual service acceptance criteria, which is frame delay, variation, jitter, loss, availability. So each one of these services are unique to themselves when we set them up. And that specifically emulates then network traffic as we're going to put network traffic across it. So the easiest way to think about this is that like a leaky bucket. You'll hear people say leaky bucket analogy. So I just want to take a second and kind of explain what the heck is a leaky bucket analogy. So here say we're at a substation, and we're going to generate what's called ingress traffic. This is traffic that's being pumped into the upstream network. It's ingressing the network. And so here we're going to come in, and we come into our pipe, and it drops into a bucket. Now, a certain amount of data is allowed to flow out the bottom of that bucket because it's leaky. And that information that is guaranteed to get out that bucket and get across the network without issues is what's known as the committed information rate, or CIR. And this is what we call green frames, a service level agreement guaranteed. It will get there. It will get there within the specified rate that is defined as the CIR. Burst size is a little bit more advanced. That has to do with network tuning, and Ethernet is bursty in nature. It allows the frame to burst a little bit above this committed information rate for a certain amount of time before it starts clamping and throttling it down. Now, why this is important is that operational SCADA type traffic, teleprotection traffic, and voice services absolutely have to stay within the committed information rate. We do not want them to go beyond those bounds, because anything beyond the committed information rate can be thrown away. It's discard eligible. So that's the reason why it's important. So basically, any traffic that doesn't make it through the committed information rate bucket, doesn't leak out the bottom list bucket, well, it overflows, and it overflows into another bucket. And this is what's known as excess traffic, or excess information rate. It's considered best effort. It's not a part of a pass-fail criteria when we're testing 1564. We're mainly looking at the committed information rate. This is more informational to see if the data, if it went over the excess information rate, how much did it go over, but not necessarily did it get thrown away, did it get through. And so in this case, we can use the analogy of non-operational traffic, email, maybe some of your CCTV frames. Maybe they're allowed to burst over the committed information rate, because generally the whole network isn't using the whole pipe. So we do a little bit of sharing. This goes back to that frame relay type mentality of the legacy transport, where we share a little bit of that excess information, and only if everything sends at once and it gets congested, then we start throwing frames away. So as long as everything plays nicely, it still gets through. But we wouldn't want to send teleprotection information over here, trip and reset type information, relay information, and have it be able to be thrown away by the network. Would not be a good day. So lastly, anything that is ingressing into the network and overflows this excess information rate bucket immediately goes in the garbage can. Okay, it's what's known as a red frame. It's overflow. Never makes it in, never makes it out of the substation into the network, because we don't want to congest the network with information that should have never been ingressed anyway. So your newer routers and switches on the, mostly routers, in your substations, they're hardened routers, have what's known as traffic policing. And so it's constantly monitoring the traffic and saying, is it a green frame? Is it a yellow frame? Hey, it's outside of both bounds, throw it away. Don't even let it get into the network. So that's the reason why we use the leaky bucket analogy, because if you think about it that way, it's easy to see where in the path do things get thrown away. So if we go back and think about the bandwidth profile, then here's our data pipe. When we think about our committed information rate is the green pipe. It's guaranteed. It has its own individual slot in the pipe. It's guaranteed to get through. Where our excess information rate is kind of shared. And then if we go outside those bounds, that becomes a red frame and it never makes it into the pipe and immediately gets thrown away. So we'll talk a little bit more about this as we go through the committed information rate and excess information rate. Color mode and coupling flags a little bit more advanced for this conversation. We'll circle back and maybe do advanced Y1564 training later if folks ask for it. But it's good information to know as you tune your network. When we think about the service acceptance criteria, or the SAC, now we've already defined how much data gets through the pipe. Now we're talking about the quality of the data going through the pipe. What's our frame transfer delay? So if those folks are used to saying latency, guess what? New acronym, frame transfer delay. That's where we define it through the MET, the Metro Ethernet form. Where frame delay variation, which is jitter, is how the frames go through the network, how consistently do they go through. And why this is important is obviously for VoIP and some sensor traffic is very sensitive to jitter. So we want packets to come through at a very consistent basis. You also define your maximum acceptable frame loss and your service availability. How long is that service up without disruption? And if it is disrupted, how long is it disrupted? So this is your service acceptance criteria. So now we talked a little bit about what's a bandwidth profile, what's a service acceptance criteria, and how would we use Y1564? How does it work? Let's go through and let's look at an actual smart testing example. How would we physically use this in a real-life network as it pertains to a smart grid? So the Y1564 test procedure, there's basically four steps to follow. So first we have to define what's our service level agreements. And if you're a communication service provider, they have well-defined service level agreements. You're going in and you're buying a pipe that is a certain size, that has a certain service level agreement, latency and jitter, and so they're selling packages of these pipes, these data pipes to their customers. Probably not as well defined for utilities. These are still sensor networks that are evolving. Working with the major vendor equipment manufacturers will help determine what's the maximum throughput will be consumed by this sensor. What's the maximum latency will it be allowed to support, or jitter will be able to support. Obviously from an operational standpoint, how sensitive are you to any type of service disruption? So those service level agreements for a utility needs to be set up by the utility. There's general guidelines I'll provide here based on my knowledge of the network and pulling some information from other sources, but really the service level agreement is defined by the utility itself and becomes kind of that corporate-wide document. So once we define what that SLA is, then we have to tell the test equipment, what is that SLA? What are we testing for? How are we going to send traffic? Where is it going to go to? And what quality of service and class of service do we want it to be tested for? Once that's configured, hook up all the gear, start the test like any other piece of test equipment, and get all our results back, do some troubleshooting if required, create the test report, everything's done. So if you look at it from an RC 2544 standpoint, about the same. Really the same steps you'd go through, just a little different twist. So first, if we look at our defined service level agreement, now this is non-empirical data. I just made this up based on best knowledge. You can kind of use it as a reference, but don't use it as an absolute standard. But the idea was just give you an idea of here's a whole bunch of different types of data that goes across your network, either from substations or going to network operation centers. And here's some changes, or here's some differences. So if we think about committed information rates, your high-speed protection data is typically a very slow but reliable network, 64 kilobits, 128 kilobits, very slow data. We absolutely do not allow it to go into the excess information rate bucket because we want it committed to that green frame. And it actually has very low frame transfer delay. We need low latency and we need low jitter, and absolutely can't lose at the 0.1% frame loss ratio. So it can't have frame loss that exceeds a certain threshold. And of course, 5 nines availability. Service always has to be available. We can also define different VLANs if you're using VLANs for your operational, non-operational, segmenting out your traffic flows. You can also set up your VLAN and your priority as a service level agreement as well. And as we go down, you can see very, very sensitive network elements all the way down to your voice and PBX, where your flow's a little higher. It's allowed to kind of go into that yellow zone. The latency is a little higher, and your jitter's a little higher, and maybe you don't need it up 5 nines. Maybe that service is good enough to be up 99% of the time. When we talk about over a year, service disruption that's 5 nines is less than, I believe, 5 minutes of disruption in a year. 99%, maybe the service isn't available a half an hour out of the year. So, maybe that intranet type data, okay, if it's not available, it's still important, but maybe not as important as our real-time operating system data, right? So here you can define your own unique service level agreement for your protection sensors, video IP security, voice, and intranet, and completely separate those out into different service level agreements of what you're willing to tolerate as far as performance across your network. So now that we do that, the first step is with your test equipment, we have to actually set up. Now we know what our service level agreement is. How do we translate our table into actionable data? So we take our test equipment, and the nice thing is that most of the equipment, all the equipment that Greenlee has, if you have an existing configuration set up, you can recall that. Because most of the time your service level agreements, if you go from substation to substation, it's not the SLA that changes. It's the destination of the data that you're sending that changes. So why not just recall a previous test, make a few changes. You can actually save multiple profiles. So, substation A versus substation B. So if you go back periodically and test these services again, just recall them and away you go. But obviously, the next thing we have to do is we have to activate our configuration and performance tests. And so when Y1564 works the same across it because it is standardized, but your configuration tests and performance tests are separate. You may only want to perform a performance test once if you're going back periodically and doing testing. You may not want to do a configuration test anymore. You just want to test the actual performance of the network. And you can also set up, by default, it's 15 minutes. That's the standard of ITU. T1564, but you can change that all the way down to 5 seconds if you want to. And then the next thing is we have to start setting up the actual, goes back to talking about the service layer. Is it a layer 2? Is it using MPLS? Is it using VLAN? You know, those type of things. And actually 1564 is all based around layer 2 frames with VLAN, not specified for MPLS yet. I expect it's probably going to have an amendment, and it'll move on up to a layer 2.5, 3 type test as well. You'll set up each one of those because of each one of the different sensor streams, in this case 8, you'll have 8 different choices. You can have a layer 2 frame go to one destination. You can have a layer 3 frame go to another destination. You can duplicate the same frame and have it go to another destination. So now you can emulate sensor data going to 2 separate locations simultaneously. But you go through and you configure all that information. And then move on to your bandwidth profile where you're actually setting what's the committed information rate, what's the excess information rate. If it's not being used, it's unchecked and it's grayed out, and then that way you don't allow the system to send any type of excess information on that particular stream. And then we configure our performance or service acceptance criteria as well. What's the maximum delay? What's the maximum jitter, frame delay variation? How much frame loss are we willing to accept on this service? And what's the minimum availability, should it be? So it takes a little bit of setup the first time you do this because we're now testing individual sensors. So to gain extra visibility in your network, there's a little bit more configuration. But definitely you'd save that as a profile and you never have to do it again. And then the last thing is typically you set up what's called a ramp. So where RSC 2544 is that fill the pipe all the way up, see if it breaks. Y1564 has a little different mentality. It says, let's ramp for slow and make sure it goes at a certain minimum rate, then let's ramp up to say 50%. Okay, and let's ramp up all the way up to what the committed information rate is. And then if so configured, if excess information rate is specified as well, we'll send excess information rate as defined right here and see if that goes across the network too. So, you know, the standard is that you always test the 3 steps. You do 25% or 33%, 50% committed information rate. You can make that as low as 1 if you want. You can go directly to committed information rate if you want, or you can add 15 steps, up to you. By standard, this is pretty much standard as far as Y1564. So now that it's configured, next thing we have to do is actually perform the test. So once the test is started, the actual performance test, the configuration test is the first thing that runs. And what it's going to do is it's going to take each individual service and step through it and run that bandwidth performance, the service acceptance criteria, and it's going to say, does this stream, this flow, meet the service level agreement for what was defined when we set up our SLA? And then once all the services are tested, the next thing it's going to do is it's going to combine all those into one big test, and it's going to simultaneously send, in this case, 8 different service flows, so 8 different sensors, operational traffic, non-operational traffic, VoIP, IPTV type traffic, and it's going to send it to multiple destinations if you configured it as so, and you're actually treating it now as a true in-service type test. But because each one of these are set up per the sensor requirements, we're not taking a 100 megabit pipe and putting 100 megabits across it. We're actually taking and only sending that information that was configured across that network. So in this case, we may have only been sending, say, take a look here, you know, 5 megabits to 10, 12 megabits, depending on what we configured. So we're not using up the full pipe. So now you're able to keep your in-service traffic running and still test, say, new sensors going across the network without consuming all the bandwidth and having to wait until a maintenance window opens up. You can actually do this real time if it's set up properly and configured properly. Once the test is all done, then what's going to happen is the system's going to come back and it's going to give a completed service configuration test and show what the performance data is across all of it. Are all these services passing properly? If only one service is working and the other 7 are getting dropped, that's an indication that something isn't configured in the substation or the network properly to do the traffic flow and to have all those services simultaneously. we would know if a particular service was failing here, if the service was configured wrong. Here it tells us, is the network configured wrong, because we're able to send all those flows simultaneously. And then, of course, at the end, just like on RC 2544, we gather up all the test results. You save it as a particular test result, different names, different location information, be able to put the location and tech information in, and that becomes part of that birth certificate for that location for those service flows. And so you can actually take the test results now and take a completed test report, export it out via PDF or raw information if you want to pull it into your own system. You can even FTP it up. And what you end up with is another report that's just like RC 2544 that you're used to seeing, where you have all the information across your network service flows with nice graphs that shows exactly what happened on a per flow basis or per service basis, and also all the services going simultaneously. So it's a much more comprehensive report than you would get with RC 2544 because it's customized for that location, for those services you're sending. So in summary, the smart grid transformation is definitely underway. You're seeing it. Everybody's seeing that smart grid is the new big buzzword, has been for about 5 or 6 years. Some folks are getting tired of hearing smart grid, but it's a more intelligent grid then. But we're improving our operational efficiency. We're reducing costs, modernizing the infrastructure with putting in more advanced sensor networks, migrating to an all-IP network, an MPLS. And the reason why we're doing that is that networks are evolving, and they're now multi-point type sensor networks, mesh type networks. They're using a lot more path diversity. There's a lot more point sources of where they're coming from. And so if we look at RC 2544, it's just not designed for testing smart grids anymore. Sure, from a point-to-point standpoint, limited capability. It has some uses. It can be, the settings can be tweaked to kind of work, but really not designed for testing multiple service flows. And that's why 1564 really is smart testing for the smart grid. It's testing multiple service flows to SLAs. You're verifying individual class of service and quality of service metrics. You can perform it in service if it's configured properly. And then you can also provide detailed reports and provide service level agreement birth certificates as well. So much more advanced from that type of standpoint that you can emulate true sensor flows going across the network, not an entire pipe.